manipulation group, together with Karma Torres. The topic of my talk today is about presenting the different applications that we are providing to the robots in the assistive domain. Let me share my presentation. This one. Okay, so let's go. So as I said before, as Karma said, just a very brief presentation. We do robot manipulation in human environments with these three sub-objectives, and the idea is that we combine AI, robotics, machine learning, computer vision. We are using all these technologies in order to put robots in human environments. Mainly today I'm going to talk about the assistive robotics, so in human environments, in social environments, or hospitals, or daycares, or at home. But at the end of the talk, you will see that we can apply also these technologies to industrial environments, because basically it's the same. So the story is that robots were inside of the industries, then we started to put them outside, so without the fences. So we had to develop all this technology to make robots safe. And now industries have realized that this is very interesting, so they try to put this technology back to the industry. So first example I'm going to talk today. I'm going to talk about 4 different areas, and they are linked to the 4 different projects that we are currently doing. The first one is robots for cognitive training. This is an European project called Socrates, and this is an overall concept. So let me show you the video. It has a nice sound, but I believe that you cannot listen to it, so you can see the subtitles. So the idea is, yeah, we need robots for elderly people. And our idea is that robots should be a tool for the caregivers in order to help them provide better treatments. Here, the use case is clear. So Alzheimer patients do exercises to make cognitive training, so keep their mind healthy. So Alzheimer, it's something that cannot be cured, but we can stop or slow down the decreasing curve. So this is how it's done now. So you have one person with one patient doing the test, but as you know, there is a lot of patients and not that much people. And this kind of exercise is quite repetitive. So why don't we try to do it with robots? And this is how we envisage that it should be done. So the first caregiver programs a robot, and this is very important. The robot is not autonomous at all, but it's programmed by the caregiver. But once it has been programmed, it chooses what to do based on these different sensors. So he has a camera, and we have a rate sensor, and the kind of help that the patient is providing depends on all these inputs. So you see, again, we can make a robot that it's introverted or it's extroverted, depending on the preferences of the person. And this is going to be important. Another thing is that if we do that with a robot, then we can do it anytime. So the person can do this exercise as many times as he needs, even at home. Yeah, we don't need the caregiver. We don't need the caregiver for doing this, but you see that always we are asking the caregiver for help every time something happens. So this is envisaged as a tool and not a replacement for the caregiver, okay? And just make a little bit of fun, you see that, yeah. This is how we envisage that it's gonna go. Okay, so this is how it goes. What we envisage is that the robot has these different engagement levels. You see a level 0, which is instructions, level 1, level 2, and level 3, and level 4. So every level is increasing the kind of help, and how we choose what the robot has to do. So every time it has an interaction, which level has to choose, it's decided on several inputs. First one is the difficulty of the game. So you can see that the difficulty of this game changes over time. In that case, at the beginning is very difficult because you can choose among all the different tokens or all the different letters. And as you go towards the end of the game, there are less tokens left, so you have less tokens to choose. That it becomes easier. Then also the patient history. We know if this particular person has difficulties on particular tokens or letters, if he gets distracted easily or not. So we also use the patient history. So this is tailored. The patient condition. So one of the things that we ask to the caregiver is to provide, which is the patient condition, if he has a very advanced Alzheimer or disease, or it's just a mild one, or even no mild disease. And also we left 1 degree of freedom to the caregiver, because sometimes the caregiver chooses that the patient has to be challenged, meaning give the patient a little less help than it's required, so he finds the task a bit difficult. Or engage the user, meaning the user is, I don't know, a bit bored, so you have to try to engage the user so he continues doing the exercise. And with all this information, this is how our system looks like in reality. So this is our facility. This is our assisted living lab. You see we have 2 different robots, 2 Tiagos, and we are using one of them for this task. This is the board, and you see the numbers. So we set the exercise to order in ascending order these kind of tokens. This is our patient, and this is our caregiver. By the way, it's myself for the video. And so this is the programming, you see. So now we have programmed the robot, and we said, okay, this is the condition of the patient. I want them to engage or not, or neutral. And let's start. So the patient, you see, has some difficulties finding the first token, and the robot just says something. This is the message that he says. That in that case, don't worry. So he's not really helping now. He's just engaging, as you can see. Okay, and but here is providing some help. You see, look here. Okay, instead of looking at all the board, just look over there. This is a 1 level help. Okay, he did well, but the robot decides that he has to provide again some kind of help. Yeah, and here you say this is level 2. This is like, no, pick this one, because I see that you have make a lot of mistakes. So this is the right one. And we have even a 4th level of engagement is this one. So it's just giving you the pieces, this one. It may seem that it's providing a lot of help, but if you observe real similar patients doing this kind of task, this is the kind of help that they need. Okay. So how we do that? You can see on the right side of my slide, we have different layers on our robot. So we have the perception layer to know how it's how is the state of the action. We have the behavioral level. There's the one that decides which kind of help it has to provide. And for each one of the levels, it can be only speaking or speech help or speech plus gestures. And then we have the execution layer. And you can see that then we decided to go on the wild and make a real experience. This was in a study, This was in a study with 29 people in a public event. So you see our robot just doing the real task, or by using all these different layers. And one thing that it's nice to observe while you are doing these real-time experiments is that you see this person, for example, needs some kind of social acceptance. You see it's talking all the time with the guys, yeah, you look, I'm doing well, or I'm doing bad, or something like this. And the other thing is that sometimes the help that we are providing takes a lot of time. And this is why we had to accelerate a little bit the video. You see that this video has been accelerated. It's per 5. And this is because everything is a bit slow at this moment. Okay, let me show you a little bit some results that we had from this experiment. First hypothesis was that participants that received the assistance from the adaptive robot, so the robot that tries to figure out which is the best help to provide, would perform better than the ones that did not receive assistance. Okay, this was our objective. This is our first result. So you see that this is a reaction time. And on the x-axis, what we have is the different tokens. So we had 5 tokens here. You see 1, 2, 3, 4, 5, and marked with some marks. And this is the average time to move each one of them. And you can see that here, sometimes there are mistakes, sometimes there are not mistakes. And what we can observe is that the average time of the people using an adaptive robot is much less than the people using a non-adaptive. And regarding the number of mistakes, it's the same. So the number of mistakes regarding the people with adaptability, it's much less than the number of mistakes people but with non-adaptive help. And something interesting is that at the end we also asked them for their opinion on the use of the robot, and all the people was positive. You see that they found the robot likable. They did not find it distractful. They said that it was comfortable and that they think that a robot like this may be useful. And this was an exercise of thinking about what this robot could do in a real environment, because obviously this was an experiment, that it was some kind of a mock-up. So this is not a real experiment with a real product, but people made this effort on thinking about this technology could help, and everyone found that it was positive. Obviously, of course, we also tested other hypotheses, and I let you see the paper if you are interested and see which was the answer. But the lessons learned here were that immediacy was important, so we took a lot of time to provide the help, and that social acceptance was also important. So let's see what we did about immediacy. So we changed the face of the robot by this new face that we designed with the screen. You can see in this picture that now our robot has a screen with face. These are the type of faces that we devised. So sad, confused, angry, neutral, or happy. And we design all these faces to provide non-verbal, non-gesture, because gestures take a lot of time, immediacy of help. That does not mean that the previous help is not there. It continues to be there. But now we provide 2 different assistances. So one is as soon as we detect that something wrong or something good happened, okay? And if the person is not using this input for nothing, so he continues to do the action, then we rely on the old one, so the robot still speaks and the robot still moves, okay? To have this immediacy, what happened was that perception was not that reliable, so we switched to this board. You see that these tokens are on a board that is disconnected because they have RFID receivers at every position, so we know exactly at the moment that the token has been lifted, that which token has been grasped, and then we can provide this immediate assistance. And for measuring the social acceptance, what we did, it was a social. So we created this model. You see that the intention of use, it's our main goal, and we see how this intention of use is affected by these other variables, like the perceived usefulness, or the ease of use, the enjoyment, the social influence. You have seen people looking at the rest of the people saying, yeah, look, it rocks, or it's cool. So how this feeling affects the intention to use the robot, and so on. And we did a user study, this time with 130 people. And these are some of the conclusions, as you can see on the links. Okay, that the social influence has a positive effect on the intention of use. That the perceived enjoyment also has a positive effect on the intention of use. The perceived ease of use, though that was one of our hypotheses that was not validated. You see, it's not directly linked to the intention of use, but it's indirectly linked to the intention of use through this perceived usefulness. And this is something that I'm going to talk a little bit later, and it's about how we measure our robots. So it's cool, we do cool robots that do nice things, but now we have to measure them. And as soon as we put people into the loop, these measurements become a little bit harder. And robotics, yesterday you saw a lot of measurements using these vision algorithms, these nice algorithms that we are doing. And somehow they have found a very nice way of measuring this. They have these databases, and then they can say, okay, this is, I can locate, I don't know, the 83% of the dogs on my database. But in robotics, it's not that easy because we have robots, and robots manipulate the world, and there is a lot of uncertainty here, and you are going to see that it's much more difficult. And for this kind of social robots, again, it becomes a bit difficult to measure all these hypotheses that we have. And what we are doing on the group is exploring the social models in order to provide an objective measure to this technology that we are creating. Another thing that we are doing is trying to use simulators in order to learn, because, okay, I've been talking about robots deciding what to do based on different criteria, but how we are doing this. And the way we are doing this is sometimes using planning algorithms. So what we do is we handcraft our planning models, and we handcraft our cost functions. Okay, so you have a cost function with a lot of parameters, and we try to tune these parameters in order to the robot behave the way we want. Sometimes what we try to do is to learn this. So we don't handcraft these cost functions, but we know which is a good decision or it's a bad decision. Sometimes it's with the help of the caregivers themselves. And then we train these algorithms against something, and we learn the policy. And this something for us is this kind of simulator. And this is how it looks, our simulator. We take from psychology theory one concept that it's called persona. And persona is like a mock-up of a person. So you say, okay, this is an old person. It has this kind of difficulties. And this creates like a model of the person. And we use this model to train our decision-making algorithms in order to learn the policies. And we believe that in all these social interaction activities, with these variables, it's enough, because our simulator just provides if the action that was expected was chosen by the user or not, and the time that it took to take this decision. And we are using these 5 different parameters. This is the reactivity, the attention span. This is very important because this the attention span is directly linked with the time that the person is taking to react. The hearing, because that means that maybe it has some difficulties in some of the modalities that we are using to provide this help. The personality trait, and safety risk. So people, it's very scared of robots, and others are not. And this also influences the way they are reacting towards the robot. And if you are interested, we published a paper talking about this, and we emphasize that this is not useful only for this kind of games, but this can be generalized for other kind of tasks. The use of simulators is not that yet extended on the social robotics community or in the assistive robotics community, because there is this belief that simulating the behavior of the people, it's quite difficult. And in fact, it is. But we believe that there is no other way if we want to use this kind of artificial intelligence algorithms based on data. Okay, this is about the Socrates project. Now I'm going to talk about other kind of activities that we do, feeding and dressing. Karma on the talk before has showed you a couple of videos. I'm going to show you them again, but just pointing out different importance or different things. So the first one is this about putting the shoe. So what I want to highlight here is that to be able to do this, what we have to do is to fill the gap between the high level planning and the low level execution. And this is something that it happens all the time in robotics. Here, exemplified as a social or an assistive task, but it happens all the time because we have a plan, and the plan is in the symbolic level. Your plan is put the shoe on the feet, and to put the shoe on the feet, you have to do several tasks, and you can decompose this task in, let's say, symbolic steps. But then you need to execute this. And to execute this, you need to be adaptive to the current situation on the scene. And this is two different worlds, and there is a lot of information in the middle that we don't really know if should be on the high level. So for example, where the food is, this is something that the planner should know and should plan taking into account this, or this should be on the low level, saying the planner just say, grasp the food from wherever it is, and the low level is the one that decides, okay, now I have the perception and I decide this and that. And depending on what you want to do, one solution is best suited, and depending on what to do, the other solution is best suited. So this is what we did in this paper. This is the gap. So you see the high level planning. And level. The low level is that we have this, in this case, there were demonstrations that were able to adapt to these different positions. But there were some parameters that were left to the planning. For example, when to speak. Okay, so for some people wanted to know everything that the robot was doing, but this is taking some time. So for some people, it was more comfortable just do the task as fast as possible, meaning the robot should not talk at all. And for example, for velocity, it was important also. It's like if the robot moves too quick, I get scared. So I remove the foot, and then the task takes more time because I have to ask the person, hey, put the foot again inside of the workspace. Okay, so you see on the right side of the slide this high level and low level, how it's implemented in our case. High level was based on planning this time, and this is representation of all these different actions and the preconditions and the post conditions. So from where I can go to where, and which is the cost. It's embedded in the links among the different tasks. And when one of these tasks was decided, how this was executed. In our case, it was by doing several demonstrations, so we could adapt these trajectories to the different positions of the feet, for example. Okay, and this had some advantages. For example, as we were using planning, we had not to be aware of planning all the unforeseen situations that happen. Okay, so for some of them, some of these links are not specifically handcrafted on the model, but they come because of the construction of the planning model. Another thing I would like to talk is in feeding, and an important feature that we need, that it's safety, because look, we're putting things inside of the mouth of the people, and here safety, it's a must. And this is a good example, because every time we put robots on human environments and we touch, and you have seen that we like a lot touch things and touch people, then safety becomes a priority. Okay, and Karma has talked about all these different situations when the face is not looking, or when we touch and we measure the maximum force, and there is a standard that says which is the maximum force that we can exert if something unforeseen happens, and we proved in this paper that we were below these maximums, and all of this. And I would like to talk you about these kind of preferences. Okay, so we have seen putting help dressing shoes. We have seen this help feeding, and we say that all the time that we are adapting. But we are adapting to what? So as it was a bit difficult to answer this question, then we decided to create this kind of taxonomy, and we published that some time ago, 3 years ago now, where we had this preference taxonomy, and we decided that we had like 2 different kinds of preferences. One was for the decision making. Yeah? So when the robot has to decide what action to do, it can rely on very different information. And imagine this is a situation. So you have the robot, the robot senses what's happening on the environment, and now there is not a unique action that it can perform. So the robot has to choose among different options, which is the most beneficial. And formerly, most beneficial meant the quickest one. So I want to finish the task as quick as possible. This is the usual criteria. But now that we are among people, this is not the unique criteria. Safety, as I said, it's another criteria. So maybe there is a quick action, but it's not as safe as the slow action. But preferences are another criteria. So people prefer robot talking a lot, or people prefer that if it's alone, the robot acts in a way, but if it's with company, if there is other people around, that acts another way. For example, in feeding, in feeding, if you are alone, maybe you want the robot just feed you as fast as possible. But if you are with other people and you are talking, you don't want the robot to bother you with the spoon in front of your face, So there are some social cues that have to be made in order to make the robot choose the right action at the right moment. On the other side, we have this other configuration, and it's about the physical. So I want the robot to approach the spoon, but not in any way. For example, I prefer the robot go slowly, or I prefer the robot go quicker, or exerting forces. So I don't care if the robot it's a bit more stiff, or I want the robot to behave more compliantly. And this is like modifiers to our actions. We are approaching equally, but we are approaching in a different manner. So it's not about choosing the action, but it's about choosing the way we are performing this action. And this is where the two different kind of preferences are we detected, and we try to make a taxonomy of these. And in the paper, you can see different examples for these particular applications of feeding and of dressing. And in dressing, we envisage two different applications. One with this shoe dressing, but the other one that we use only one robot. But the other one was this jacket dressing, where we have seen that we are using two arms. And here the variability is much more higher, because you can start with one arm and go to the up, and then the other one, depending on the mobility of the arms of the person. Then you cannot. So some of the strategies are not possible because the person has not mobility. So all these kind of preferences or physical limitations play an important role there. And here are examples of what I've said. So you see, these are different executions of the same task of feeding, but you can see in each one of the videos, the robot is behaving differently. For some of them, the robot is talking. You see, it appears a message there. For some of them, the person is not talking, the robot is not talking. For some of them, the robot does not put the spoon inside of the mouth, but waits till the person approaches. For some of them, the robot puts the spoon inside. And for the shoe example, it's exactly the same. For some of them, the robot goes quick. For some of them, the robot goes slowly. For some of them, the robot talks. For some of them, the robot exerts more force or less force. You see, some of them have already finished. Some of them are slower. So now they finish. And you see that the robot sometimes just the person just keeps moving. So the robot, considers that the task is not finished and continues trying to finish the task. And here is the same for this example of the two-arm task. In our case, it's putting a shirt on a person, and this is the same. The robot just adapts to the mobility of the person and the preferences and so on. And how we are doing this is, as Karma said, using ROS. This is the overall picture of our robot and all the different models that are involved. The planner, we are using probabilistic planning. In this case, it's an RDL representation. So we participated in adding this probabilistic planning in ROS-Plan. ROS-Plan, is the framework for semantic planning in ROS. It had some non-probabilistic planners there, and what we did, because all these tasks require to handle probability specifically, because there is a lot of noise involved, noise in the perception, but also noise in the action. So every time we perform an action with a robot, we don't know if whether this action is going to be successful or not. So we have to tackle all these probabilities in the planning. Yeah, and this is how we do it. And you see that there is all this closed loop about sensing, putting these sensors on the knowledge base, using this to deciding on this asking some actions. And these actions are intelligent in the sense that I told before. Sometimes they already know where the foot is. So the action is at the high level planet, at the high level of saying, grasp the object, and the action already knows where the object is, for example. But there are some parameters like the velocity or the maximum force, all this combination that I told before. Okay, now let me talk to you about benchmarking a little bit more, because this is important. So we are in a project that it's called BURG, and this is a project about benchmarking. And our role here is benchmarking of textiles. You have seen that we like a lot to manipulate textiles, garments in particular. So at some point we said, okay, we have produced all these algorithms about looking at them or manipulating at them. We know that it's difficult because every time you manipulate a garment, it changes its shape. And later during the day, they are going to talk you about all this complexity. Here, I'm going to talk about how we want to benchmark this, in the sense that we need to provide measures to compare. Otherwise, you have papers saying, okay, yes, this is my robot and this is how it does the things, but we don't know if this is better of another approach, or in which situations this is better or not. These are the tasks that we have envisaged on this paper. We have a paper on benchmarking manual cloth manipulation. You see we have 3 tasks. One of them is putting a tablecloth. The other one is folding a towel. And the other one is putting a t-shirt on the head. Why these tasks are important? These are important because we need 2 robots to perform these because of the size of the clothing. You can see that in literature, there is some approaches to manipulate garments, but usually they are small garments because the kind of robots and the kind of workspace of the robot that you need to manipulate big garments, it's somehow different, and this is a challenge. So we decided to start by this because this is something that it's going to receive a lot of attention by the scientific community in the next years, because this is really a challenge. You not only have a clothing that it's already challenging, but you have a big clothing that is more challenging. Okay, so let me talk about what we had to do in order to provide some measures to this. First of all is set the initial conditions. So initial conditions means we have to normalize the kind of objects. So we said, okay, this is a tablecloth that we are going to buy, and make sure that anyone can buy this more or less worldwide. So we decided to go for IKEA tablecloth and putting exactly which one. So making sure that this is the tablecloth that it lasts more on IKEA catalog, and that everyone can buy one of those for its laboratory. And another thing that it's very difficult is the initial state. You see these 3 pictures on the bottom side of this rectangle. These are the 3 different initial conditions that we envisage. First one is folded. Second one is crumpled. And third one is flat on the table. Flat on the table is clear, okay? This is very easy. But the other 2, although it may seem easy, they are not. For example, take the folded one. Okay, imagine that I want to say, okay, I have an algorithm that can unfold tablecloth, for example, and I test it on my lab, and I just buy this IKEA thing, but I have to specify how I fold it, because it's not the same folding, one way or the other. The way the way it deforms while unfolding is very different and can really affect the output of the algorithm. So we have to specify how we fold it, how many times we fold it also. But look at the example on the middle, the crumpled one. This is even harder. How I crumpled something that is repetitive. how I can say my algorithm can deal with crumpled textiles, because I proved, I repeated 3 times on my lab, and look, this is my results. Because there are a lot of ways of crumpling things on the table. Some of them are easier. For example, this one on the feature is easy, and it's easy because you can see that there is a very visible corner that it's laying on the table. Okay, this is easy. But if this is not the situation, if the corners are not laying on the table, then it's a bit more difficult, because maybe there are visible corners, but maybe there are not visible corners. Okay, so that's just to say that it's very difficult to provide a measure to say these initial conditions. And now we have to provide the measures, and this is a measure that we propose for this tablecloth thing. So we propose that we measure all these distances that you can see on the figure, and there is a formula on the paper that says, okay, based on these 3 different measures, you have these quality functions. Okay, and you can see that we have this grid. Okay, because we can have these different initial conditions, and these are more or less these are the measures that we proposed for this task, and these are the measures that we obtained on our lab, just trying to do this with a very simple algorithm. And the very simple algorithm is this one. Okay, so we had this sample thing. As you can see, one of the corners was on top on the table. This was our specification. One of the corners lying on the table. We have this by manual setup, but this is not something that everyone wanting to compare to us has to do. So the robots can be whatever robot you want, and the position of the robots can be your proposal. Okay, the benchmark is not imposing anything on the kind of robots or the kind of data sets. Our solution was this one. Okay, so grasping from one corner and then going from this to the other corner. Usually, when the tablecloth is smaller, the second corner is visible, so you can just go there and pick it. But this tablecloth is quite big, you can see it. So this was not an option. So we had to do this strategy of edge tracing just to reach the second corner. And now you can see that once the 2 robots have both corners, then they execute this linear motion in order to spread this tablecloth on top of the table. And this was our proposal to solve this spreading tablecloth task. And the numbers I showed you before, and they were presented on this paper on RAL, on the Robotics and Automation Learners. So we did it 5 times. We said on our benchmark that we had to repeat these 5 times and take the means of all of this. Okay, although this is a quite difficult task. And my last.
Excuse me, Guillem.
Yeah.
I think you have a question. Can you see?
Okay.
Can you see the chat?
No, because I have my complete.
Okay, this is the question by Muhammad. How do you measure these distances in an automated way?
Yeah, that's a very good question. So our benchmark, the table is specified, so you already know which is the distance and everything, because you already know which is the size of the tablecloth, and you know which is the size of the table itself. So you already know. But of course, a generic method would require to sense all this. And you have seen that we have no sensors on the grippers of the robot, but we are working on this. So now our next step is try to physically put some sensors on the fingers, so we are able to not rely on knowledge about the size of the garments, but being able to use any kind of garment. Yeah, I think that this answers the question. Okay, then let me continue. My last example is how we are now trying to put all this technology on industries, and we are coordinating this Symbiotes project, and this is about putting robots in industry. And we envisage this collaborative task, and this is a collaborative task where the robot and the person share forces. You see, again, we are touching the robot, and the robot holds something, so the person can polish something. You have seen that to communicate things with the user, we have used these lights on the wrist of the robot. So these wrists have some meaning. Okay. The robot does not know if the person, it has to hold still, you know, because the person is polishing, or it has to change the position, you know, or it has to release, you know, and we are using forces in order to understand which is the thing that every time the user wants. For example, this. Yeah. Okay, to do that, well, we made an experiment with 15 users, and we have all the results on the paper that I mentioned. How torque forces from the force sensor look like? They look like this for the 3 use cases. These are, let's say, profiles, but we started playing a little bit more dirty with the robot, meaning that some of the signals were not that clear, because we were interested in seeing how many times the robot get wrong when we tried to do something and the robot just understood something different. And this is our solution. So the state space is huge, because we are taking a window of all these sensor readings, and basically the complexity is too high. So we just decided to make a latent variable representation of all these, and this is what it looks like, our latent representation, the 3 first variables of our latent representation. And you can see that it makes a pretty nice job just separating the 3 of the different tasks. So every point here is a different experience, and the colors are the ground truth about everything. And you can see that there is some confusion, but the latent variable representation makes a nice job doing this. But of course, we had to try also with deep learning to see what happened. And this is what happens when we try the same thing with deep learning. You see that the example that I show you is the red columns on this graphic. What we did was changing the window sizes, meaning that for the previous example, we had to wait until we had a window, and once we had a window, then we could decide. And this is what happens for the different windows. For the red column, you can see that if the window is too short, then the reliability of the method is not that good, and it becomes good more or less at a window of half a second. Meaning we have to wait half a second to get some readings from the sensor, and then we can decide. So the reading took for sure more than half a second. And what we did, it was trying with LSTM or GRU, that it's, you know, the network that it's for this temporal coherence. It's a new version of GRU, or is the new standard for this. And we realized that for both of them, even using a window that it was very little, we could obtain very high reliability. You can see in the window of 10 milliseconds or 20 milliseconds, or 100 milliseconds or 200 milliseconds. This is the window size. The reliability of the method is quite high already. This is the times. So you see with the GPLVM that I showed you before, we took like a little bit more than 1 second to take a decision. With dynamic time warping, that is another method that it's more or less based on the same idea of taking windows. This time was quite less, and the precision is a bit higher. But with deep learning approaches, the 2 GRU and the 2 LSTMs, you can see that the time that we devote to make the decision is much more or less than in the 2 other methods, and the probabilities or the quality of the prediction is quite high. And let's see what happens with this confusion matrix I told you. So this is grab, move, and polish for each one. You see in the diagonal that methods were quite good at doing these, and that the most confusions were when it was grab, but the system thought that it was move, and when it was move, the system thought it was grab at the same time. Okay. This is not work that I did myself. This is work that it's collaborated with a lot of people, a lot of PhD students and postdocs now at IRI, and with the perception manipulation group. This is the principal ones, but there are a lot of students also that help. And also these are collaborative projects, meaning that we did not all the work or alone. So we collaborated with a lot of people because we have some very established collaborations with other groups that allows us to make more that we could do all alone. And that was all from my side. I think that I have some time for some questions left. So just, I'm open for questions now. Thank you so much.
Thank you, Guillem. I think we have a question by Muhammad. Muhammad, are you there? No. It's fine. Okay, okay.
Okay, I believe that I'm the only thing between you and the coffee break. So maybe people is eager to have a break.
Okay, I think so. So thank you very much, Guillem, for your presentation. And okay, we will return in 15 minutes at 11:15 with a new presentation. Okay. Oh, here we have a question. Can you see it?
Yes, I can see it now. Okay, yeah. Then the question is, could you explain if you have used any human feedback technologies such electroencephalography? Yeah, we have tried to do so, but the kind of signals that you can obtain from electroencephalography or these kind of sensors that you wear in a helmet, it's quite noisy. This is something that we tried sometimes, but with not real results. What we are using now is this heart rate sensor, because sometimes when people get nervous, heart rate changes. So we are trying to use this as an input to take decisions. And obviously we are using the obvious ones, that it's a camera that is looking to the person. And if the person is not looking at the board, for example, for the cognitive training, we assume that he's distracted, and then we don't wait till the timeout to say something. When we see that the person is just looking around, we just try to get their attention again. There is some software that from the facial expression can provide you with sort of affective assessment, like person is happy or person is bored or a person is scared. But usually this software, it works very well with very extreme facial expressions. And when people is in front of our robots, they are not really scared, making a exaggerate scaring expression, meaning that this kind of software, again, it's quite noisy. And if we change our decision based on these, what happens is that sometimes we make bad decisions. So we keep trying. I have to say we keep trying, because as much information, as much inputs as we have, the better. But we have not found yet any of such technology that can be used. Okay.
Okay, thank you, Guillem. Thanks a lot, say Mark.
Okay.
Thank you very much. We will return at 11:15. Thanks.
Bye, thanks.